Why do scientific findings seem to contradict each other? One week something is good for you, next week it is not. Is science broken? Not exactly. But there is subtle statistical trap that can make completely ordinary research look like breakthrough discovery. It is called p-hacking, and it does not usually involve fraud, cheating, or bad intentions. In fact, most p-hacking happens when researchers are trying to do careful, thoughtful work. Welcome back to Sheetal's Data Desk. I'm Sheetal, and in this video, we will unpack what p-value actually means and what it doesn't, what p-hacking looks like in practice, why running multiple tests increases false positives, and walk through a simple demonstration showing how completely random data can appear significant. Why p-hacking is so tempting, from psychological biases to publication pressures. Practical ways researchers can avoid accidental p-hacking and strengthen their work. And finally, we will step back and look at what this means for science as a whole and how to think critically when you encounter surprising results. So, let's begin with foundation, p-value. Before we can understand p-hacking, we need to understand one key idea, p-value. P-value answers very specific question. If nothing interesting were happening, if there were truly no effect, how surprising would this data be? Imagine flipping a coin 10 times, 5 heads and 5 tails, completely normal. 6 heads and 4 tails, still normal. 10 heads, that would be surprising. P-value measures that level of surprise. In many scientific fields, researchers use threshold. If P is less than 0.05, result is called statistically significant. That means if there were truly no effect, you would expect to see result this extreme, less than 5% of the time. That rule sounds reasonable, but there's important condition attached to it. It assumes you tested one thing once. Humans rarely do that. And that's where problem begins. So, what happens when we test one thing more than once? P-hacking happens when researchers explore multiple ways of analyzing data and only report versions that produce statistically significant results. No fabrication, no falsification, just flexibility. Imagine you are studying whether sleep affects exam scores. You could analyze all students, only freshmen, only students under 21. Remove outliers, keep outliers, control for stress, ignore stress, use linear model, try non-linear model, compare by gender, compare by major. Each of these choices create different statistical tests, and each test carries its own 5% false positive risk. Now imagine running 20 variations. Even if sleep has zero effect, probability suggests that one of those tests might produce p-value below 0.05. Not because relationship is real, but because randomness occasionally produces patterns. If only that significant result gets reported, research now tells distorted story. Not because data was fake, but because path taken through data was selective. To see why this matters, we need to understand how probability behaves when tests multiply. P-value of 0.05 means if there is no true effect, about 5% of the time you will see significant result by chance. But that is for one test. If you run 20 independent tests, probability that at least one appears significant rises substantially. Random variation begins to look like meaningful signal. This is sometimes described as fishing for significance. The more lines you cast into the water, more likely you are to catch something, even if lake is empty. Now let's make this concrete. Let's imagine simple demonstration. Suppose we generate completely random data. 1,000 fictional people, random sleep hours, random test scores. There is no relationship. Now we try multiple analyses. Linear effect, quadratic effect, remove top 5%, remove bottom 5%, split by gender, add control variables, apply transformations. Eventually, one model produces p equals to 0.03. It looks statistically significant. It looks publishable, but it is also entirely false. This is the core danger of p hacking. It transforms randomness into apparent discovery. But here's the important question. Why does this happen so often? Most p-hacking is not malicious, it is structural. First, the garden of forking paths. Data analysis involves countless small decisions. Should we remove that outlier? Should we control for age? Should we log transform that variable? Each decision seems reasonable, but collectively they create hidden multiple testing, even if you did not intend to run many tests. Second, publication pressure. Science rewards clear conclusions, positive findings, novel effects. It does not reward inconclusive, no evidence found, effect was small. When significance becomes currency, pressure to find it increases. Third, human psychology. We are pattern seeking creatures. We naturally see structure in noise. Statistics exist partly to protect us from that instinct. But when flexibility meets curiosity, false positives can slip through. Fourth, zero point zero 0.05 cliff. Difference between 0.049 and 0.051 is tiny, but professionally it can feel enormous. That sharp boundary encourages threshold chasing. So, if incentives and psychology are real, how do we reduce risk? Solution is not abandoning p values. It is reducing flexibility and increasing transparency. First, pre-registration. Before collecting data, specify your hypothesis, your primary variables, your model, your exclusion rules, your planned sample size. This separates confirmatory testing from exploratory discovery. Second, clearly distinguish exploratory from confirmatory work. Exploration is valuable, but exploratory findings generate hypotheses. They don't test pre-specified ones. Third, adjust for multiple testing. If you run many tests, use corrections such as Bonferroni adjustments or false discovery rate control. These reduce inflated false positives. Fourth, report all analysis. Transparency prevents selective storytelling. Fifth, increase sample sizes when possible. Small samples amplify volatility. Larger samples stabilize estimates. Sixth, share data and code. Reproducibility is one of the strongest safeguards against accidental bias. But even with these tools, there's broader shift required. P-hacking does not mean science is broken. It means science is human. Curiosity drives discovery, but curiosity needs guardrails. Modern reforms, pre-registration, replication efforts, open data are strengthening those guardrails. Science is learning to examine its own methods. That's a sign of maturity, not weakness. So, what should you take away from all of this? When you encounter surprising study, ask how many analyses were tried? Was hypothesis specified in advance? Has result been replicated? Is the effect meaningfully large or just barely significant? Statistics alone does not protect us from being misled. Good research design does. P-value is not a villain. Unexamined flexibility is. Explore boldly, test honestly, report completely. That's how we protect both science and our thinking. If you found this video helpful, don't forget to like, share, and subscribe to Sheetal's Data Desk. Thanks for watching, and I'll see you in the next video.